Yeah, so before the break we were stuck with this complex problem, and the coffee helped to find a solution, hopefully. So what is the solution? So again, we have the 4-bar mechanism. Ta-ta. So what is the solution? What is the most powerful instrument of the engineer? Scissors, right? So let's apply some scissors. If we cut open the system, so if we make a open loop system of the thing, then we can sort of solve it. And then the only thing we have to do is we have to add some constraints to close the system. So the solution is cuts to open the loops plus constraints to close them again. Because for these open loop systems, it's pretty easy to write down what the expressions are, right? So if we now have this open loop system, so the first bar like this, the angle was alpha, right? Then the second bar like this, and then the third bar on purpose I draw it open, because here was a support, but I've cut it. I opened the whole thing. Then here we have beta, and here we have minus comma. And of course here we have the center of masses, length is A, B, and C. And then let's put numbers, this is body 1, body 2, and body 3. Now writing down this expression xi is ti from qj, no, that's not a q, from qj, is now with, I made two cuts, actually, a horizontal cut and a vertical cut, so my qj is now enlarged. I have alpha, beta, and gamma. And I have a nice open loop system, and I can just write down what the expressions are. x1, that remains the same, of course, cosine alpha, y1, a over 2 sine alpha, but then, and phi 1 was this alpha, but then x2 is this a cosine alpha plus, and then I can write easily b over 2 cosine of beta. Likewise for 2, for the y direction, b over 2 sine beta, and the angle phi 2 is this beta, and finally x3 is a cosine alpha plus b cosine beta plus c over 2 cosine gamma, etc. That's clear. You can easily write that down. But we, of course, have to add constraints. We cut the loop, so the constraints are actually that in this point D, I think I call it D, A, B, C, C, and this is D, that the delta xd should be 0 and the delta yd should be 0.
One quick question.
Yeah.
What would be phi 3? Is it minus gamma or plus gamma?
Oh, yeah. You would think that relativity is difficult, right? Or particle science. It isn't. It's easy. The most difficult topic in science is plus and minus. That's really very hard. and also here. So what do? I write minus gamma here, meaning that if the thing is up in a positive direction with respect to the horizontal axis, plus gamma. Yeah. Or you could say, okay, I put in minus gamma in the expressions here. So I write here cosine of minus gamma, yeah, and then the cosine of minus gamma is equal to the cosine of gamma. But I wouldn't do that. I would just look at the figure and say, oh yeah, if this is minus gamma, then plus gamma is up.
But V3 would then be minus gamma.
Right. I would say gamma. Okay, I'll put it in to be super clear. Phi 1 is gamma.
3.
Yeah, 3. Phi, what did I write? 1 plus 2.
Thank you for that.
Thank you. Yeah? Okay, and how do we find these expressions for this delta? Well, then we have to go over the chain and say, well, this x here should be identical to this x position here and the y there. And in our case, that comes down to, well, again, this chain, A cosine alpha plus B cosine beta plus C cosine gamma minus, and then the horizontal distance of this point with respect to this. This was the origin. Thank you, Heike. Minus, and the distance was D, is 0. And then the vertical one is, of course, with the sine alpha plus B sine beta plus C sine gamma. Yeah, plus 0 or minus 0 is 0. So those are then the two constraints. So we have enlarged our degrees of freedom, but we have to add those two constraints to come back to the system. So in the end, we still have 1 degree of freedom. And that is the thing we go about, because now it's super easy to write down the equations of motion. And so the constraint equations of motion have then this form. We have this mass matrix, we have this Jacobian, and here this Jacobian 0. Then we have our Q double dots here, we have our lambda vector here, and we have our right-hand side. And the right-hand side is, yeah, generalized forces Q with a bar, right? And then we have all these convective terms, and I never know how to write them. C comma Q, Q dot, something like that. How do we find the M bar Q double dot is Q bar? Well, that's super easy. That's in our whole system with the TMT method, right? The lounge in Rotterdam. So that is, how did it go? We had a mass matrix Mij, and then we have to pre and post multiply it with this Jacobian, and the Jacobian is Ti, K. No, that is then a J, right? And a post multiply, that's a Ti, okay, L. So the outcome is a K and an L, and then times Q double dot K is, and then we have Q L, because the L is the output here. Minus, then again we have this transformation matrix Ti, L times applied forces minus M I, J, and these were convective terms, J and, or did I call them H? Sometimes G, sometimes H, I don't remember. Anyway, this is easy. This is we've done that in the previous homework assignment. So this part we can determine. This part, this is this Q bar, and this is this M bar. We can easily determine. The constraints is also simple by differentiating them with respect to our generalized coordinates, and forming these convective terms is also not that hard. So in the end, then we have a sort of reduced system, not completely reduced, but partly reduced, which we can easily solve. Now, how does that go? Then from these equations, so from the equations of motion, we solve for the unknown Q double dots at some instant in time. Did I give it an index? No, yeah, and of course we also get our lambdas. And then the next step is, of course, well, maybe I put it in Shall I put an index qj and lambda k? Then the next step is, of course, to integrate. So we find a new position q. Yeah, I'll drop this one. This is not so nice. So this makes it not so clear. Q1 being at T1 is then this Q0 plus h times Q dot 0. And maybe we do the same for the velocities. Q1 is Q dot 0 plus h Q double dot 0. And so we solved at the 0 configuration. Now, that's all very fine. But now if we check, these are estimates. You've seen in your previous homework that if you use numerical integration, it's always an estimate. There's always some error. So since these are estimates, if you then put these values in the constraint, so if you then calculate what is ck of q of this q1, then probably it's not equal to 0. It's probably it's a small number, but still non-zero. And to be in a legitimate configuration, we like the coordinates to fulfill the constraints. So we want that Q1 fulfills the constraint. Now the error is of course small. I mean, you make a small error in the constraints, and then if you calculate what is the difference, then there's probably a small gap. And as an example, we've seen it, I think, in lecture 1 or 2. If you do this numerical integration with the constraints, you see that slowly things are falling apart. Slowly gaps are coming into the system. And then you would think, oh, I take a smaller step size. And yes, indeed, and then the gaps are smaller. But still, if you proceed, the gaps will grow in time. And it all has to do that you have like this differential equation q dot is 0, but it's not 0. Q dot is epsilon, and then you integrate with time, and then you can get q is epsilon times t. So you see it's a linear growing error. And you want to get rid of that error. So we have to do something. After this numerical integration, we have to fix our new coordinates, fix q1 such that they fulfill the constraints, that's really 0. So how do we do that? Maybe there goes a picture by that. You could say that the constraints, that's like some curved surface. Something like this.
Close the folder?
Oh yeah, close the folder. No, not close it.
Yes.
Zip it. So the constraint you can see is like a surface. We are constrained to be on Earth. So the Earth is surface is usually curved. And we start from some solution here, Q0, which is perfectly okay. It's nicely on, we are on Earth, no problem. Then we integrate ourselves, and then we see, oh yeah, we see that the Q1 is here by some numerical integration method. And Q1 is not on the constrained surface. So this is what we call constrained surface. So how do we want this Q to be on the surface here? And you see, of course, the error is small. It's not so big. It's not as big as the step we took. There's a small error. So we could say this Q1 is an approximation, right? It's with a tilde. It's an estimate. And the real Q1, where is it? Well, maybe here, or here, or here, or here. I mean, we have an infinite number of infinity solutions which are on the surface. So Q1 is somewhere here. Where? And then the question is, what are we going to do? Well, a intuitive way, a religious way again, is to say, well, you project it on the surface, the shortest distance, and that's probably the smartest way to do. So how do we formulate that? Well, we say we have this estimate, this Q1. and we want to have a Q1 which fulfills the constraint. So we want C Q1 to be 0, right? Then we say, well, if we now take the difference between this Q1 and the real solution, we want to actually that the norm of this one is minimal. And what is our free variable? Well, this one is given, right? So our free variable is our Q1 with respect to this Q1. So this must be a minimal solution. So seek where is Q1 on the server such that the distance between Q tilde and Q1 is minimal. Well, that's a well-posed problem. But we also have to fulfill, of course, our constraints in that sense. Q1 must be on the server, so we have to write and C Q1 is 0. Now, for those who are in optimization and so on, this is clearly a minimization problem with a constraint. Constraint optimization, we call this. And we can rephrase it by saying, well, actually we want to calculate what this distance is. So then we say, well, we can write Q1 as is Q tilde plus some delta Q. And it's actually this delta Q which we are seeking. So if you then put that in the equation, you get, the norm. I should make really a norm of this. So the norm of this delta Q should be minimal with respect to this delta Q1. I used the 1. And the delta Q still has to fulfill the constraint. So still we have the equation C of Q tilde 1 plus delta Q1 is 0. Now, this is a nonlinear problem, and these nonlinear problems are hard to solve. So the solution usually to nonlinear problems is to look in the vicinity, linearize your problem, and then with that linearized approach you do a number of steps and then you find the final solution. So we linearize our constraint, linearize it, and of course this already tells us that I want to linearize it. So we say, well, if we linearize, we get CQ of the solution plus C comma Q, the Jacobian, times this delta Q1 is 0. So that is our constraint equation. Or you can reformulate it by saying, I have some matrix, a Jacobian, times my delta Q's is minus this. Yeah, and actually this is the error you have, the error in the Q tilde. That's this distance here. That's a small number, and you want to fix that small number, but you want to fix it in the Q's. And therefore you have this Jacobian here. And this is your linear constraint. So this is your minimization problem with a linear constraint. And the name which goes by this is we solve it in a Gauss-Newton process. So Gauss is the minimization. So this is a Gauss-Newton process. And Newton is the linearization. But it's constraint minimization, and then you can write out the whole stuff, or you can read Langsos. I think it's also very nice in the book of Langsos, and I always write that wrong. Lang with a C and a Z. In the book of Langsos, what is it? Variational methods in mechanics. It's in the list of in the reference of the book. If you do this constraint optimization, then the equations to solve are like this. Again, you get a set of linear equations. Well, we want to solve our delta Q, but of course we have constraints, right? Now, and then we have a multiplier, and our delta Q has to be minimal, so the derivative has to be 0. And then we get but we have to incorporate the constraints, and lo and behold, we get this well-known form. So this should be 0, because the sum of the squares of all the delta Q must be minimal, so the delta square should be 0 under the constraint of these linear equations. And then, of course, we have as a second set the linear equations. Times this is minus the value at the current position. And this system, which of course looks a lot like all the system up till now we did with constraint problems, also in mechanics, because in mechanics our minimization problem was we minimize, it's like work, where we find the stationary value for the work. Again, that's written nicely in Langsas. Not the topic of these lectures here, but and then we end up with the same type of equation. Now, from this, we know we can solve it. Although there are zeros here, if C has full rank, then it should be able to solve these equations. Yeah?
I don't see where the first equation comes from.
Okay, the first equation comes from this. This equation, and let me write it out. So again, I go back to 100%, yeah? So if we say the norm of delta Q should be minimal with respect to delta Q. Yeah? That means actually, if you write it out, that is the square root of delta Q 1 squared plus delta Q 2 squared plus all the number of degrees of freedom I have is minimal with respect to these delta Q i's. Then, well, what does it say? Then, if it's minimal with that, we have to differentiate with respect to that. So we get 1 over the square root times 2 delta Q1 plus 2 delta Q2, etc. is 0. Or in other words, we get the sum of the delta Q, the delta Q1. And then if we do it with respect to one of the variables, we get delta Q1 is 0. And the next equation is delta Q2 is 0, right? So that is the minimal solution. And that's obvious because if this should be minimal with respect to the delta Q's, well, the minimal distance is if everything is 0. But, however, in this taking this variation, we also have to take into account that we have constraints. So we get this times this is 0, but we also have to do lambda times our Jacobian. Yeah? So that's how the constraints come into the equation, and that's how we get this 0 equation. I think it's nicely written down in the book, so read about it. Anyway, these are the set of equations which we're then going to solve. And actually, they're pretty easy to solve. Let's do a shorthand notation. Shorthand notation. So we're going to drop all the indices and so on. Then the equations look something like this. Identity matrix, a C transpose, and a 0. And then here we have deltas, a vector of deltas, and a vector, what did I do? A vector of mu's. So now it's nice MATLAB language, right? 0, and here I have an error, minus E. And what was the error? Remember, if we put in the delta, if we do fill in C delta, we get this error. So that's to remember. And we want to get rid of that error. Can we solve this equation? Well, actually, it is sort of super easy because in the first equation, it already tells you that delta plus mu times this matrix C is 0. Or in other words, the delta is minus C times these multipliers. We don't know what the multipliers are, but... And then we put this into the second equation, so we substitute it here. So we get C transpose times the delta is, because there's a 0 here, is minus E, the error. Substitute this stuff here. And then what we get, CT with a minus times C times mu is minus E. Or in other words, C transpose times C times this mu is E. Okay. Now, this looks like a matrix, C transpose times C, which is a square matrix, and the size is the size of the multipliers we have. So, and since C is there are no dependent rows in that, C transpose times C should be a regular matrix. It's only rank deficient when C is rank deficient. But if the constraints are all independent, and C times C transpose times C is a matrix which you can solve. So we can write mu is C transpose C minus 1 times E. And then what is our delta? Well, we just substitute that in our equation and we get delta is minus C transpose C power 1 times E. So now we have found a nice way to, given what the errors are, and given what the Jacobian of the constraints is, to solve for our increments. And these increments are really the minimal distance in that sense. Now, if you follow this, then you think, that is like magic. I mean, I have an undetermined system and there is a way to solve it. Well, let's do an example. And we take a linear case, because that's a bit simpler. Then it's like there's a one-step Gauss-Newton process. And the problem is such: this is the set of equations I like to solve. Minus 1, 0, 0, minus 1, 1, times x1, x2, x3. Yeah. And they are, yeah, these are actually the constraints. They should be 0. Linear constraints, very simple. So C x is 0. Yep. Now, by some magical process, I found an approximation for x. And the approximation for x turned out to be the following thing: 0.9, 1, and 1. I mean, this is the result from some process, right? If I put that in the equation, so if I calculate what are the constraints, and I have two constraints, then the outcome is 0.1 and 0. So there's an error, right? That's not equal to 0. And now the big question is, what do I have to do for delta x such that x is x tilde plus delta x, such that this delta x is a minimal solution. This delta x is a minimal distance. To this previous solution, x tilde. No, to 0 in this case. The sum must be 2 x tilde. Okay. Well, the answer was, of course, in our solution which we wrote. Like, we have to form this solution. Delta x is apparently, what was it? Minus, was there a minus sign? Yeah. Minus C times C transpose times C to the power minus 1 times E. So that's apparently the answer. So let's calculate the thing. So the first thing we have to calculate is C transpose times C. Well, if this is the C matrix, right, then C transpose times C is, yeah, shall we write it out? Okay, minus 1, 0, 1, minus 1, 0, 1, and then minus 1, 1, 0, 0, minus 1, 1. I did do something wrong.
Must be C.
C times C transpose, yeah. Bugger all. It's not a good day today. Yeah. C times C transpose, yeah. Okay, C times C transpose, so we get rid of this whole stuff. This one, we write it here, right? And then we make this goes away, and then we pick up this stuff, and we move it here. Yeah, okay, now we're back in business. Oh, no, go away, yeah. Here a dot, equals. Okay, so this row times this column, that's 1 times 2, And then this times this is minus 1. This times this is also minus 1. And this times this is 2. I'm sort of happy because symmetric, eh? Yeah. And it looks like it's full rank. So then the inverse of this guy is, oops, I learned a rule with the determinant. So 1 over the determinant of the thing, that is 2 times 2 is 4, minus 1 is 3, right? 1 over 3. And then again 2, 2. And then, is it plus 1 or minus 1? You see, it's again the plus and minus problem. Everywhere it pops up. You know almost the solution, but for the sign. So let's check. If we just then multiply this with this, we get 4 minus 1 is 3 divided. Yeah, that's okay. Yeah, so it's the plus. Okay, so that is the inverse. Then what do we have to do? Times the error we have, and the error was apparently this one, and then a minus sign in front of them, and times c. So delta x is minus, and this should then also be the C transpose, right? Otherwise that won't work. Minus the C transpose, 0, 0, minus 1, 0, 1, minus 1, 0, 1, times. And then out of my head, I'm going to do this times this. But that's super easy because it's 0.1 and 0, so it's only this first column. The second you can discard, so it's 0.1 times this column, so it's 0.1 times 1 over 3 times 2, 1. Okay. Then what is the answer? So we have to multiply this with this, and that's minus 2. Yeah, so that's 0.1 times minus 2 over 3. And then the second one is 1 over 3. And then the last one is minus 1 over 3. Yeah. And you may remember from the quiz, this is the shortest distance for the thing. If you calculate what the norm of this guy is, then the norm of this guy is, what is it, square root of 6 over 9. And that's less than 1. So the norm of this delta x is less than 0.1. Yeah. So you would think that making the new solution, let's write the new solution. So that's 0.911, and then plus this delta, which is 0.2 divided by 3 with a minus sign, 0.1 divided by 3, and minus 0.1 divided by 3, and then the answer is, there's a sign error, I guess. There should be a minus here. Again, the minus and plus. But the answer I get in the end is, of course, all identical. It should be all identical numbers. And they are all identical. 0.9 and then 6. 0.9 and then 6. 0.9 and then 6. And that answer is, of course, clearly closer than another solution would be, an obvious one. Solution would be if you say, oh yeah, it's 1, 1, 1, right? That also fulfills the constraint, because actually these equations tell us that x1 should be equal to x2 and x2 should be equal to x3, or in other words, all the x's should be equal to each other. 1, 1, 1 is also a solution, and you would say, oh, that's close to this one. No, this one is closer. Yeah. So this shows how this method works, this Gauss-Newton process, and we call that in our system, we call this coordinate projection method, because remember the picture we had here in the beginning, that we have this constrained surface. So we had a solution here, we had a solution here, we have an approximate solution here, and how do we get back to the surface? Well, by projecting to the surface. So by taking the normal to the surface, and then fitting that in that Q tilde and say, oh yeah, in this distance we go down to the surface. Perpendicular to the surface we go back, so we project it on the surface, and by such is the distance then also minimal. And this is actually the process we apply in our constrained multibody system, minimally constrained multibody system. How does it go? And the algorithm now for our coordinate projection method goes like this. Yeah, let's say the coordinate projection method goes then like this. And I'm going to write an algorithm. That's sort of fun, I guess. So first you set the number of iterations to 0. Why do we do that? Well, it's an iterative process and we don't want to go on forever. We want to say after 10 iterations, if you're not home, then forget it. Then there's something else wrong. Somebody tinkered with your computer, or your cable is broken. Then we set some tolerance because, well, we will never get to 0, right? In an iterative process, it's all smaller than some number. So we set some tolerance, and well, I take a number 10 to the minus 12 or something like that. Then we set the solution we want to have, Qn plus 1. We make it equal to the approximate solution. We say, well, that's the best we have. We have this solution. And then we set our maximum number of iterations we want to do. We set that to 10. I mean, a Gauss-Newton process is a second-order process. It's a linearization. So you throw away things of the order delta squared. So it should converge pretty rapidly. Well, the first step is you evaluate, of course, what is my error. So you evaluate what my C of my Qn plus 1 is. And we give it a name. We call it E, the error we have. So we have evaluated that number. Then I make a loop. So we make a loop in this case. We do a repeat until somewhere. And what is the repeat until? Well, let's calculate what the increment should be. Delta Qn1 is minus C transpose times C transpose to the power minus 1 times E. That's the thing we're going to calculate. Oh, I didn't make all vectors out of it. Oops. So now we have calculated this increment. So we update our thing. So we say, oops, not delta. We say Qn plus 1 is this, the Qn plus 1 plus the delta, n plus 1. And then, of course, we have to evaluate, to calculate again what is our error. Our error is put it into the constraint, C Qn plus 1. And then when do we stop? Well, of course, until the error is small enough, until the norm of this error is less than this tolerance, or we are out on the number of iterations. So we have to say iteration plus iteration is iteration plus 1. We have to add up the iterations, or the iterations is larger than max iterations. And then we stop. And then at the end, of course, you can say, oh, if I jumped out of the loop with the max iterations, then I should give a warning sign or a bell or whatever. Stop the process. So this is a nice way, this scheme, to get your coordinates back on the surface. However, we also have speeds, right? We not only have coordinates, but we also have speeds. We also have approximations for Q dot n plus 1 with a tilde, right? How do we do that? Well, exactly, of course, in the same manner. The process is identical, but for the iterations, because this is a constraint problem, but our constraints, remember, on the velocity are c, q times q dot is 0. And these are linear equations. And for linear equations, you have ping, a one-step solution. So it's just one step, and then bang, you have your delta q dots, and then you add it, and then that's just a one-step solution. So this process is Gauss-Newton. For the coordinates, you have to do a number of times because of the nonlinearity in the constraints on the coordinates, but the constraints on the speeds are linear, and so you can do it in one step. And that's what we call the coordinate projection method. I want to spend 5 minutes on this book. Let me check. Then you can build. Oh. This book. It's heavy. It looks like the book from Sinterklaas, right? So what is the book? Actually, in the book they mention this paper of Talbourdet. And the title of the book is Analysis of the 4-bar linkage. And it's by Rones and Nelson. And it's actually cool. It's a book, it's not a book like Lagrange, because the book is full of, it's full of pictures, right? So it's, in that sense, it's the book Alice will love. It's the beautiful book. And what is a book without pictures? This is a book only with pictures. So what is the whole purpose of the book? Well, let's look at the title again. Analysis of the 4-bar linkage. This was the way how, and when was it published? It's from MIT. And Rones and Nelson. Rones was a professor of mechanical engineering at MIT, and Nelson was an assistant professor. So he was a slave in this work, and it's from 1951. So the book is, yeah, you would say it's old, but from a mechanical engineering thing, it's not so old, 1951. And the book is about, analysis of a 4-bar linkage, right? With a lot of pictures. Now here I have some pages from the book. Again, this is the front page. The idea is that if you work for the shoe machinery company and you want to design a machine which stitches a shoe or cuts a sole or does some motion, repetitive motion, then you use a 4-bar linkage. But in designing, you know what the output is, you know what the motion you want to have, but you don't know what the mechanism should look like. So it's like this inverse problem, and it sounds a little bit like integration and differentiation, right? Well, that's true. That's the whole book. It's a table lookup book. So let's go to some pages. So here is a page, and here you see curves. And these are what we call coupler curves. So this is one of the bars, and then we take a point on the bar somewhere in that. I should point. So you can make a plane. You can attach a plane to this middle bar, and then you can add a number of points on that plane. And then, as a function of this input motion, you can say how does that point move. So if this rotates, then this point, which is part of this rigid body, so you have to imagine there's a rigid body attached to this bar, moves like this. Let's take this point again on this rigid body. How does that move? It goes like this. So if you are looking for a motion, you just flip through the book and then you pick a curve which you like. But there's a lot of information in these graphs. Not only do you see what the x and y of the curve, but it's dotted, and the dots have a meaning because the dots are equally spaced on the input. So from knowing that the dots are equally spaced on the input, you know that then the dots on the output give you information on speed. So if the dots are very short, then the speed is low. And if the dots are larger, then the speed is higher, right? So it gives you already a little bit information on that. How are these curves generated? Well, you would think with the formulas, right? That's also mentioned in the book here. Here you see these formulas, and these are exact formulas which I showed the Tauboudet paper with the analysis. However, they're not made like that. They're made with a mechanism. They're really made with a thing like this. Yeah. So to design a machinery, they make a book with coupler curves to designing your machinery, and the coupler curves in itself are made by a machinery. Right? Okay. Now we are in a class, it's 2019, right? No, 2019, that's sort of fun. Yeah, 2019, and as a homework assignment you can do this easily in MATLAB. Take you 2 hours or something like that. Compare that to writing a book of so many pages, 1951. So you see a little bit the jump we made also in engineering in a scientific way. Okay, see you all next week, hopefully without any technical problems. I'm sorry for that. Yeah, stop the recording.